Hello students. Hello students. So our last class was finished with this diagram, and I told you that the state of matter does not depend upon that enthalpy and internal energy, enthalpy or internal energy, and it depends upon that free energy. So let us start our today's class with a new topic. And our today's first topic is bound energy. Bound energy. Or it is also known as entropy factor. Bound energy or entropy factor. So what is bound energy? This energy is bound to the system. This bound energy is bound to the system and it's not available for doing any kind of work done. This bound energy is not available for doing any kind of work done. And I already have told you that this bound energy is also known as entropy factor. So this entropy factor is equal to T into S. The product of T into S. T is temperature and S is entropy. So the product of temperature and entropy is known as entropy factor. So you all know that entropy is denoted by S, and this S is equal to integration of Cp by T dt from 0 to T. This is entropy, and entropy at 0 Kelvin, entropy at 0 Kelvin temperature is 0. So if entropy at 0 Kelvin temperature is 0, temperature is also 0, then that means entropy factor also or bound energy also will be 0 at 0 Kelvin temperature. So in other words, I can say the material has certain internal configuration. All the materials, all the materials have some certain internal configuration, and to that configuration certain energy is involved. Okay, so this energy which is involved with that configuration is called bound energy. So what is bound energy? This bound energy is always bound to the system, and it is involved with the configuration of the material, Every material has certain internal configuration, and this bound energy is involved with that configuration. So now we shall talk about solid structure. Solid structure. What are the different solid structures? One is crystalline structure. Another is non-crystalline structure. So, in this case of that crystalline structure, it is in a regular arrangement and periodically repeating pattern. This crystalline structure, it is in a regular, it is in a regular arrangement, and this arrangement is periodically repeating pattern. This is crystalline structure. And what is non-crystalline structure? So I can write it over here. Regular arrangement and periodically repeating pattern. This is crystalline structure. So non-crystalline structure means structure similar to liquid. Structure similar to liquid. So these two types of crystal structure, solid structure is there. So one is crystalline structure. What is this is this having regular arrangement and periodically repeating pattern, and another is non-crystalline structure. This structure is similar to the structure of liquid. So these two solid structure we do have, and I think this two is very much clear for all. Now we shall talk about difference between three states. Difference between three states: solid state, liquid state, and gaseous state, by means of by means of motions, by means of motions of atom. Okay. So we have three kinds of motions three kinds of motion. So there are three kinds of motions any atom can have. So what are those three types of motion? First is oscillatory motion. Second is rotational motion. Third is translation motion. Translation motion. So these three kinds of motions any atom can have: oscillatory motion, rotational motion, and translation motion. And among these three kinds of motions, uh, oscillatory motion, this oscillatory motion is the only motion which is available in the atom of solid state. Oscillatory motion you can find in only the atoms of solid state. Any solid states, no any liquid, no any gas is having this oscillatory motion. And at 0 Kelvin, there is no motion you can find. At 0 Kelvin, no motion is available in the atom. So, when solid is about to reach at its melting point, some rotational motion can begin at that time. Otherwise, rotational motion you can't find in solids. So rotational motion is not a characteristics of solid state material. So at a solid state, you cannot find that rotational motion. Only when the solid is about to reach its melting point, then some amount of rotational motion can begin at that point. Otherwise, it is not available in solid state. Liquid and gases have that rotational and translation motion. And atom in crystalline solids are atom in crystalline solids. I have already told what is crystalline structure or crystalline solids. So atoms in crystalline solids are oscillating about a mean position or fixed position of the atom. Okay, so the atoms of a crystalline solids are oscillating about a mean position or a fixed position of the atom with varying amplitude and varying direction. Is it clear? So the the amplitude and direction can vary, but all the atoms will oscillating about a fixed position or a mean position of the atom. And with the increase in temperature, the frequency of oscillation increases. So if you increase the temperature, then the frequency of oscillation also will increase. I've already told you that at 0 Kelvin, the frequency, there is no any motion. That means at 0 Kelvin, the frequency of oscillation is also 0. The frequency of oscillation is also 0. So whenever we are increasing the temperature, that means the frequency of oscillation is also increasing, and it increases up to 0, sorry, up to 200 Kelvin. So up to 200 Kelvin, if we increase the temperature, with that the frequency of oscillation also will increase, and after that it will stabilize. After the 200 Kelvin, it will stabilize. This frequency is called lattice vibration frequency. This frequency is called lattice vibration frequency. It is denoted by gamma, which is equal to 10 to the power 13 per second at temperature greater than 200 Kelvin. At temperature greater than 200 Kelvin. So up to 200 Kelvin, the frequency of oscillation will increase, and after that it will stabilize. After that it becomes constant, which is called lattice vibration frequency, and this constant frequency is 10 to the power 13 per second, 10 to the power 13 per second. So this oscillation energy which is available to the atom in crystal solids is referred to as thermal energy. So what is thermal energy in this case? So this oscillation energy which is available to the atom in crystalline solids is referred to as thermal energy. The so the average energy per atom, average energy per atom per mode of oscillation is equal to kT, is equal to kT. What is K? K K is Boltzmann constant. This K is Boltzmann constant. K is equal to Boltzmann constant, which is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. This K is equal to K is Boltzmann constant, and this K is equal to the value of K is 1.38 into 10 to the power 23 joule per Kelvin. And if we multiply this Boltzmann constant with Avogadro's number, then it will become K into N naught. N naught is Avogadro's constant. Then it will become universal gas constant. Universal gas constant, which is denoted by capital R. And the value of this capital R is 8.314 joule per mole per Kelvin. So this N naught is, what is N naught? N naught is Avogadro's number. Or Avogadro's constant. Avogadro's constant. Entropy. Now we should talk about entropy. What is entropy? Entropy is basically randomness of material. Randomness of materials. Entropy measures the, basically this entropy measures the randomness in materials. So what is that randomness? Randomness is the direction and amplitude of oscillation. And randomness is the direction and amplitude of that oscillation motion. So I already have told you that atoms in crystalline solids are oscillating about a fixed or mean position of the atom with varying amplitude and varying direction. So this amplitude and direction of oscillating motion is the randomness. And the amplitude is a measure of energy. This amplitude is the measure of energy. Therefore, as the amplitude is amplitude is different for different atoms. Therefore, atom do not have same energy. Atom do not have same energy which which are oscillating about their mean position. So one which have higher amplitude will having the higher amount of energy, and if the amplitude is lower, that means it will have lower energy. So when atoms are oscillating, when these atoms are oscillating about their amplitude, with their amplitude maybe may not be same as a result that I have already told you that all the atoms are having different energy, different level of energy, and due to this the amplitude also will vary. So every atoms will have different amount of energy and different amount different that amplitude. So as the amplitude is not same for all, as a result of this there may be a collision among the atoms. There may be some collision among the atoms. Due to that collision, some atom will absorb energy and some will reject. In other words, this amplitude could be vary from 0 to very high, and the direction could be also changed during that collision. So why this collision will be happen? Due to the varying amplitude or varying level of energy, for due to which that amplitude also will vary. Due to this varying amplitude of every atoms, a collision will or a collision may occur between the atoms. This randomness is associated with the thermal entropy. This randomness will is associated with the thermal entropy, which is also depends on the direction of oscillation and amplitude of the oscillation. So now I will discuss about Boltzmann Maxwell Boltzmann statistics. Maxwell Maxwell Boltzmann statistics. So I think you all know about that Maxwell Boltzmann statistics. There is a probability that an ensemble of an species has some energy which is greater than equal to probability that at temperature T, which is exponential of minus E by minus E by KT. So this probability, when we add up for all the atoms and then divided by total number of atoms available, it will give us the fraction of atoms which having the energy greater than equal to E. So this probability, when we when we add up for all atoms available in the crystal, and then divided by total number of atoms available in the crystalline solid, it will give us the fraction of atoms which are having the energy greater than equal to E. So I can write it, fraction of species having energy greater than equal to E at temperature T. At temperature T. So that's all for today's class. In our next class, we will discuss about configurational entropy. Configurational entropy. So thank you for today.